Hello, so today I'm going to explain to you what an operon is and the lac and the trip operon and the differences between them. So, first of all, I'm going to talk about what exactly an operon is. So, right here we have a prokaryote, a bacterium, okay? And then this region right here is a chromosome, one circular chromosome, a bacterial chromosome. And in these chromosomes, there's going to be DNA, and all that DNA is just in that one single strand. And basically, an operon is like a sequence of DNA in that circle, and the operon is going to determine if the genes that are in the bacteria are going to be encoded or if they won't be encoded. And that's bacteria especially needs this because number one, prokaryotes are super efficient, right? They don't waste, they don't have time or space or to waste materials and make things that they don't need. So in order to make sure that they're making enough and they're not using excess materials for no reason, they have operons. And the operons basically based on environmental factors. The prokaryote is gonna know, oh, I need this gene to be read and translated so it makes something, or oh, I have enough of this and I don't need it to be translated. And as you know, prokaryotes read DNA and translate it at the same time. Transcription and translation happen at the same time, while in eukaryotes they happen separately. So again, prokaryotes are very efficient, and basically they need these operons to tell them, do I need this the protein that's going to be made, or do I not need the protein? So how an operon works, there's going to be, these are the genes here, right? And then this is a regulator gene, which is going to make a repressor, okay? And the repressor, what it does, if it goes to the operator right there, and when it connects to the operator, here, let me draw this. When it connects to the operator, that's so messy, but when it connects to it, basically what will happen is that if a DNA polymerase tries to come to the promoter region, it's blocked and it won't be able to read the genes. And if it's not able to read the genes, then proteins aren't gonna be made, right? And then sometimes in some cases this applies to the lac and the trip operon. There can be an inducer or a co-repressor. So an inducer, let's say it connects to the repressor. If the prokaryote doesn't need the protein or doesn't need something that the proteins would make if they were encoded, an inducer would come to the repressor, and then it would change the shape of the repressor. So if it changed the shape of the repressor, that would be made instead. It would change the binding site of the repressor. So if the repressor went and attached to the operator, it wouldn't work. So basically the repressor wouldn't be able to stop the polymerase here. It wouldn't be able to stop the polymerase, and the polymerase would attach to the promoter, and then it would go through, and then these genes would be made. Why am I so bad at this? Okay. These genes would be made. And then basically, again, these genes are going to make more, they're going to make something and something. And then when they make these things, again, these could be inducers or co-repressors, something. It's going to be affecting the repressor. So let's say this kept going on and on and on in this operon. At one point, there's going to be a lot of this product that the protein is making. And again, it's going to bind to the repressor. It's going to change its shape. Or if these are co-repressors, it's going to bind, and it could help the repressor. It could change it. So again, there's different cases. That's one difference between the lac and the trip operon, which I'll explain in a bit. But it can attach to the repressor. It can help the repressor and allow it to repress what's gonna the gene and make sure nothing is coded, or it can stop the repressor and allow the polymerase to go through and read the sequence and make more proteins. So that's a rundown of an operon. And again, everything that's needed before you reach this part of the gene is going to be upstream on the gene. So the regulatory gene that makes the repressor, the promoter, and the operator are all obviously going to be before the genes, which are more downstream, because again, you need to make all of these things before you can even get to the genes, so the cell can determine, do I need to make the genes? Do I need to do transcription and translation, or should I just block it off through a repressor? So that's how an operon works, and then I'll get to Lac and Trp now. Okay, so first I'm going to go over the Lac Operon. So, bacteria has to be efficient, right? And basically, bacteria is going to, two different ways it can get energy is from lactose and glucose, right? So, preferably, it's easier to break down glucose in prokaryotes. So, if they have the choice, bacteria is going to choose to break down glucose instead of lactose. So, that's the reason why we have this cap site here, because basically the cap site will determine for us how levels of glucose will change whether or not the operon will be expressed. So the two different regulators in this operon is the repressor and the cap site. And basically the cap site is gonna be activated when there's low levels of glucose, okay? Because when there's low levels of glucose, there's a lot of CAMP, and CAMP is what activates CAP and allows it to bind. So if there's a lot of CAMP, then the CAMP will activate to the CAP, and then it'll activate to the cap site. And I'll explain what that does in a bit. But those are the two factors that determine if the operon will express the proteins, these proteins here that are in charge of breaking down lactose. Okay, so the first situation we have is if we have a lot of glucose present, but we have no lactose. So if there's no lactose and this operon, if there's no lactose present and these proteins are in charge of breaking down lactose, then it would make sense that the cell wouldn't go through the operon, right? Because we have nothing to break down. Why would we waste materials to produce proteins that would break down something we don't even have? So what would happen if we didn't have lactose? A repressor would go to the operator, like I said before, and then if a polymerase came and tried to attach the promoter and read the genes, it would be blocked. So the polymerase wouldn't be able to read the genes and start transcribing the DNA, okay? So that's the first situation. And then again, if we have glucose but no lactose, we're not going to need CAMP or CAP, because CAP only happens, the cap site is only used when there's low levels of glucose. And if there's a high level of glucose and there's glucose present in a cell, then CAMP won't be made because you don't need to signal to the CAP protein to go to the cap site, okay? So that was the first situation. The second situation we have is if we have a lot of glucose present and we have lactose present, okay? So basically low-level transcription of the Lac operon occurs, okay? So because we have lactose present, we're going to need these proteins. Sorry, I'm terrible at using this stupid iPad. So we're going to need these proteins to break down lactose because we have both lactose and glucose, okay? However, it's going to be at a low level because if we already have glucose and lactose in a cell, the prokaryote is still going to prefer to break down the glucose. And that gene, let's say the glucose operon or whatever, to make proteins that will break down glucose is going to be way more active than the lactose operon because it's not going to rely on these proteins as much. So these proteins will be made, and basically, it's going to break down the lactose using these proteins. However, again, CAMP is not being made. Here. There's still no CAMP because we have glucose. Again, glucose is only the cap site is only going to be like enabled when we don't have any glucose, okay? And then third situation, we have glucose. We have neither glucose or lactose, okay? So that's going to be this third situation here. So if we don't have any glucose or we don't have any lactose, again, the cell cares a lot about whether glucose is there first more than if lactose is there. So camp is going to be made if there's a lot of, if there's no glucose. The camp is going to attach to the cap. And then the cap is going to, it's basically, without camp, it won't be able to do this. But with camp, it's able to go to the cap site. And basically what happens is, once that attaches, sorry, wait. Okay, sorry, my dad walked in. But again, back to what I was saying. No glucose or no lactose. Camp is going to be made because there's no glucose. And camp and cap are going to go to the cap site. However, again, there's no lactose. So repressor, same thing as the first scenario. Repressor is going to go to the operator. And then a polymerase is going to be, good morning. The polymerase is going to be blocked from reading the genes and creating a protein. So that was the third situation. The final situation in which actually the most is going to be happening, okay? If we have glucose absent, so we don't have any glucose, which means we're going to be using camp, and we have lactose present, there's going to be a lot of transcription of the Lac Operon because basically there's no glucose. So the cell's like, oh shoot, we don't have any glucose. We have to only rely on lactose. So there's going to be a high amount of lactose being broken down, right? Because the cell is only relying on lactose now. So here's the thing that's going to happen when the cell isn't producing. It's going to stop the repressor. So let's say we make the polymerase attaches to the promoter and it reads through, and then end result, we have these proteins being made, right? And these proteins are going to break down lactose, okay? So the repressor is still going to try, even though we need to actually break something down, the repressor is still going to try to stop the process, okay? And the only way something is going to induce and repress the repressor itself, actually, in a way, is allolactase. So allolactase is a derivative of lactose. So it comes straight from lactose. And basically, it's formed when, as a signal for the repressor to not work, okay? So if allolactose attaches to the repressor is going to take on a different shape. Like, let's say it becomes a box now, and instead of triangles, it has a circle, right? So if we have this new repressor, it's not going to be able to attach to the operator, and it won't be able to stop anything from happening. So because of this allolactase being stopping the repressor, the polymerase is going to keep going through, and it's going to keep attaching to the promoter and reading and creating more proteins to break down the lactose because we have a lot of lactose. So again, when the cell has a lot of lactose, allolactose is going to be produced, and allolactose is going to change the bonding site of the repressor, which won't allow it to attach to an operator and stop anything from occurring. So the polymerase will be able to read through and continue this process. So, and then again, back to the cap site. So because we have no glucose, the cap site is like a red alarm. It's telling us, okay, come on, we need a lot. We need this transcription. We need to read this gene a lot because we have a lot of lactose but no glucose, right? So again, camp is going to be made because we have no glucose. It's going to attach to the cap. Cap is going to attach to the cap site. And then basically what this is going to do is the cap site is going to help RNA bind to the promoter. Like, without the help from the cap site, it looks really messy down there. Without the help from cap and camp, the promoter is going to be, the operator is going to be pretty slow. Polymerase is not going to be as efficient, and it's going to take longer to read. But if you have this activated, if you have the cap attached to the cap site, oh my God. okay, you get my point. If it's attached to the cap site, the polymerase is gonna help the polymerase do its job way more efficiently. So it's gonna read faster, and then ultimately more of these proteins here are gonna be made. And if more proteins are made, there's lactose is gonna be broken down quicker. So in that way, the cap site helps the prokaryote make more proteins that will break down the lactose because there's no glucose in the body. So basically that's an example of how bacteria how prokaryotes are efficient, because using cap and the repressor, we're able to make sure like we're doing the right thing. We're not wasting any resources. Like if we don't have any glucose, we're gonna make this much, like a lot of lactose, because we need to survive. We need energy as a cell, as a prokaryote. So the Lac Operon is again a prime example of how a prokaryote is able to regulate what it needs and how fast it needs to be done. So yeah, that's the Lac Operon, and it's 4 different scenarios. And also really quick, I wanted to make a quick point about positive and negative feedback, right? So cap site is a prime example of positive feedback, because basically the prokaryote is getting the signal that, oh, we have no glucose, so we need to amplify how much lactose proteins we're making that will be able to metabolize the lactose. So CAMP, and CAP, all of those proteins right there, they're a prime example of positive feedback, because you keep pushing the polymerase, you're making the polymerase do more work, and you're amplifying a signal in a way by telling it to produce more and more and more of these proteins. So that's an example of positive. And then negative feedback in here is how the proteins prevent the RNA polymerase from transcribing, right? So the repressor is an example of negative feedback, because it's attaching to the operator. And then although the cell naturally, the polymerase naturally wants to read and make these proteins, the repressor is going to be negative control, because it's telling the cell, okay, stop doing what you're doing and then go back to its present state. Like let's say we've broken down and metabolized all of our lactose, and we had a lot before. So negative feedback, it's going to push the cell back to normal by telling the polymerase, like, stop binding. You're not allowed to read anymore because we're done now. So it's the opposite of positive feedback. Instead of amplifying it and telling it to do more, the repressor is coming and it's stopping it's stopping the polymerase from doing more and creating these genes. So yeah, that's an example of positive and negative feedback in the Lac Operon. Okay, so now we're looking at the tryptophan operon. And basically with tryptophan, there's more proteins being made, and these proteins are in charge of tryptophan synthesis, or enzymes. So they're gonna ensure that the prokaryote is making tryptophan more quickly and efficiently. So that's what this operon is in charge of. And basically, one key difference between tryptophan and the Trp operon and the Lac operon is that here co-repressors are going to be used to help the repressor. But in Lac, the inducer is going to attach to the repressor and change the shape, and ultimately, like, it won't help the repressor, it'll stop the repressor from doing its job. So here, instead, the co-repressor, which is going to be tryptophan, which I'll explain in a bit, is going to actually help the repressor and allow it to attach to the operator. So let's talk about 2 different scenarios. So first of all, let's say we have low tryptophan and we don't have any, okay? Low tryptophan, the bacteria is going to say, okay, shoot, I need to make more proteins that are going to allow us to make more tryptophan and make it in less time. And that's what enzymes are in charge of, right? They're going to make sure that we're making tryptophan quicker and more efficiently. So if we had low levels of tryptophan or 0, what would happen? Polymerase would attach to the promoter, and let's take a second and look at our repressor, okay? As you can see, its binding site does not work with the operator, because with the tryptophan operon, the repressor needs the co-repressor to come attach to it and change its shape so it can attach to the operator. However, because we don't have any tryptophan and we have low levels of it, we're not going to have any, which the co-repressor is tryptophan. So if there's no tryptophan in the prokaryote, then the repressor won't be able to change its shape and do its job. So basically what's going to happen if there's low tryptophan levels, polymerase is going to attach to the promoter, it's going to go through no problem, and then create these proteins, these enzymes, okay? So that's case number 1. Second case, let's say we have too much tryptophan, okay? Not too much, but we have high levels. So when the bacteria notices, oh shoot, I have too much tryptophan, or I don't need any more enzymes to be made that are going to help us make more tryptophan quicker. So it's a stop signal in a way, right? So the polymerase naturally is going to go here. It's going to come to the promoter. However, it won't be able to read it, because what's going to happen if there's high levels of tryptophan, we have the co-repressor that we need, and tryptophan is a co-repressor. So what's going to happen is the tryptophan is going to come to our repressor right here. It's going to attach to it, and then guess what's going to happen? Are you ready? Boom. It changes shape. Okay? So when we add the co-repressor to the repressor, it actually helps the repressor. It's going to change its site, and it's going to become active. Okay? So this is the active repressor. So when we have the active repressor, it'll come right here to the operator, and the polymerase, oh my god. You know what? Whatever. We'll just deal with the shape. The polymerase is going to go through, but it won't be able to go through the operon and create the proteins. So that's a key difference between tryptophan and the Lac Operon, is that instead of an inducer, a co-repressor is going to come and help the repressor and allow it to do its job and attach to the operator. However, in the Lac Operon, the allolactase is actually going to stop the repressor, and it's not going to let it do the job. It's going to change its shape negatively, and it won't let it do anything. So yeah, that's basically it with the tryptophan operon. Another part of the trp operon that I wanted to mention. Okay, so there is another way that is not involved with an operator, in which a polymerase can stop working and get the signal from the cell that, hey, we don't need to make anything else, or hey, we need to make more of something. So with the trp operon, there's something called attenuation. I believe I'm saying that right. Okay, so this happens within 4 domains of the mRNA strand that is being made. Like, as you know, this is a prokaryote, that this whole process is happening in this teeny little zoom in box of the one, not strand of DNA, the circular DNA inside of the prokaryote. So in this one little circle, this is all going on, right? And basically, as you know, as I explained earlier, transcription, translation, and all of, like, everything that has to do with genes all happens at the same time with prokaryotes, because again, they're very efficient, right? So another way that a prokaryote can tell that it needs to stop or it needs to continue making something is with attenuation. So basically, with the mRNA strand that is being made by the polymerase, there's these 4 domains: domain 1, domain 2, domain 3, and then domain 4. And basically, what happens is sometimes there's like a different shape that's formed between each domain. And if there's a specific shape called a hairpin, like that kind of looks like that, but more neat. Like that. Oh, I can't do it. Okay. If a hairpin is formed between domain 3 and 4, meaning they like attach kind of and they create a loop together, then that's a sign that the prokaryote can stop, and basically the polymerase falls off and it's over. But if domain 2 and domain 3 create that little loop, then the polymerase will continue, and the strand will grow longer and longer, and it'll continue reading through the operon, okay? So in the first case, when we have high tryptophan levels, so if we have high tryptophan levels, it means, okay, like I said earlier, we don't want to make more. We don't need to make more enzymes that are going to make more tryptophan because we already have enough in the cell. So what happens is while the DNA polymerase is still moving through the strand, the mRNA in those same domains that I just went over. So if there's high tryptophan levels, a hairpin is going to form between domain 3 and 4. And this domain is basically going to signal to the polymerase, hey, you can stop now. I don't want you to keep reading, and I don't want you to make these enzymes that these genes are going to make, right, if you go through and continue. So this little hairpin between 3 and 4 is called the terminator hairpin. And then ultimately, if this is formed, then the prokaryote knows, okay, we can stop. So the mRNA will fall off of the polymerase will go away, and basically the mRNA strand finishes right there. Nothing else is made. It's a short strand, and with that type of strand, you can't really make any proteins with that. There's not enough information. It's too short. So due to high tryptophan levels, the polymerase will just fall off, and the mRNA strand is basically incomplete. However, when there's low tryptophan levels, the opposite will happen. So instead of creating the terminator hairpin between 3 and 4, 3 and 4 aren't going to create that bond, but instead 2 and 3 will. And then when it's still a hairpin, but it's a good hairpin, it's a positive one. So when this hairpin is made between domain 2 and 3 in the mRNA, it's called an alternate stem loop. And basically this is a signal that, hey, we can continue. And then what happens is the polymerase will continue, it'll read through, and the strand will keep growing longer and longer and longer and longer until it's done, and the polymerase will stop. But it'll stop way later compared to when there's high tryptophan levels. So again, domain 2 and domain 3 are going to create that hairpin when there's low tryptophan levels. However, when there's high tryptophan levels, attenuation will happen, and basically a terminator hairpin will form, and the polymerase will give up, just be like, okay, I quit, and the mRNA is going to be premature. Basically there's not going to be enough of RNA to actually make the proteins that would be needed in the situation that there were low tryptophan levels. So that's a second way. It's not really it doesn't have to do with the operator really, but that's another way that prokaryotes determine how much tryptophan is needed, and if a polymerase should continue working and make more or stop making it at all. So yeah. Okay, and now I'm just going to highlight a few key differences between the two operons and the repressors themselves. Okay, so first of all, the Lac Operon is in charge of breaking down lactose, okay? And the tryptophan operon is in charge of making tryptophan. So that's how they're opposites in a way. So the Lac Operon is a catabolizing reaction, but tryptophan is analytic. Anabolytic. No, it's anabolic. Yeah, it's anabolic. So Lac is back to unit 1. The Lac Operon is making energy because you're breaking something down. Tryptophan is using energy because you're making something. So those are the two different catabolic pathways basically for Lac and Trp. Now, regulation through the repressor itself. So number 1, Lac is inducible because when allolactase is made, it induces a repressor, and so the repressor, which is usually always active, is going to become inactive. And as you can see here, if you look at the bonding site where the repressor would attach to the operator, it's inducible because the allolactase will make the active repressor inactive, change its site, so it can't attach to the operator anymore. Whereas tryptophan has a completely different scenario. It's already inactive, and the repressor has to be activated through a co-repressor, which is going to be the tryptophan. So the repressor is only going to work if tryptophan is available, whereas the repressor in the Lac Operon is only going to work if lactose isn't present. So when lactose is present, then repressor will be turned off. But with the Trp Operon, when tryptophan is present, and the repressor will be turned on. So that's a really key difference between the two of them, which I already highlighted. So again, this kind of connects to the regulation part. Lactose, the Lac Operon is usually off. The genes are usually off because, again, if you look at the repressor, it's usually activated unless something is coming and inducing it, stopping it from working. So genes are normally off, meaning the genes are usually not read until there's enough lactose where it stops, okay? For tryptophan, it's the opposite. So genes are always going to be on, usually. So something has to come and activate the repressor for the genes to be turned off. So most of the time, tryptophan is needed to be made, and that's why the repressor is not going to be active. However, when we have enough tryptophan, the co-repressor, which is tryptophan, will come to the repressor and stop the genes and will basically turn the genes off. And then finally, just going back to feedback. So the Lac Operon displays both positive and negative gene regulation, right? This is through the cap site and the repressor. So basically, the cap site encourages positive feedback because what the cap site does is the cap site will determine how much lactose needs to be broken down, based on how much glucose there is. So if there's not a lot of glucose in the cell, a lot of CAMP, again, back to what I said, a lot of CAMP is going to be made, and the CAMP will allow the cap protein to attach to the cap site. And when the cap protein attaches to the cap site, this enables the polymerase to make the lactose, and not make the lactose, but to make lactose catabolism happen more quickly. So it'll allow the polymerase to do more and read more and create more proteins that are going to break down the lactose. So that's how the cap site is an example of positive feedback. And then again, the negative feedback is going to be the repressor for both sides, because the repressor is going to stop the prokaryote from making these genes, doing whatever to these genes, and creating something that's either going to break something down or make something. And then, basically tryptophan is only negative feedback because it doesn't have anything like a cap site. The only variable it relies on is the repressor telling it to stop. That's the only time that it receives feedback, and it doesn't get any positive feedback. Attenuation, or however you say it, is another example of negative feedback because when let's go back to this slide. When the terminator hairpin, I forgot that it's called the hairpin. When the hairpin is made, the hairpin is going to stop the polymerase. It's going to give up, and the mRNA strand is going to break from the polymerase, and it's done. So in that way, the Lac Operon contains both negative and positive feedback due to the cap site, which amplifies in a way what's happening, makes it happen more and quicker. It allows the polymerase to do more work, but it also has negative feedback due to the repressor. And then again, tryptophan only has negative feedback. So those are the key differences between the Lac repressor and the Trp repressor, as well as how the Lac Operon has both positive and negative feedback or gene regulation. So yeah, that's it.